So, ladies and gentlemen, together with my project partner from MotorBrain, we are going to present you the project or some highlights of this huge international founded project. So, sorry. So let's see what I'll tell you about this. At first I give you a short project overview. What is MotorBrain about, or what was it about? Then I come to the working fields, what topics have been addressed within this project. We come to the so-called integrated multi-phase systems. I'll explain what we understand under multi-phase systems. Before I go to highly integrated EV drivetrain system, that is what we can see after the presentation in the speaker's launch. I give you a short summary, and then I'll hand over to Michael Lambeck to give some details on the coil production and the winding production in this project. Okay, then let's come to the project overview. As I said, it was an international founded project with a total budget of more than 36 million euro founding budget, and with 32 partners from 9 European countries. So very strong and large consortium. It lasted for 3.5 years, in the middle of 2011 till to the end of last year. And the main topics in this project have been system efficiency of the whole drivetrain for an electrical vehicle or battery electrical hybrid electrical vehicle. Safety aspects were addressed, especially in electronics and power electronics development, as well as software development. Then for the hardware components, weight, volume, costs have been very important. Last but not least, sustainability was one main topic. So just a glance at the partners, the whole development chain from research institutes, universities, over tier 2 semiconductor producers to tier 1s and OEMs have been within this project, and as OEM there was Volkswagen and Fiat. Oh, sorry. Maybe you ask now, a project with 32 partners, how can this be organized? How can you achieve their valid results? Well, therefore, just a short look at the way how it was organized to understand where this 36 million euro were put. We had 8 so-called supply chains. That means always a supply chain starting from the idea, the specification, over the component development to the component integration and test. And 3 completely different drivetrains have been developed within this total budget. So not all was for this drivetrain you will see at the end. Then we had 2 supply chains dealing with energy management, energy storage, and 3 supply chains dealing with torque sensors, electronics, power electronics, and they have been integrated into the motor and drivetrain developments. So, but let's go back to the start of the project. As the title was breaking free from rare earth magnets, why was this one of the aims of the project? Well, it started in 2011. That means it was set up in 2010, and in this time rare earth magnets suffered from a very strong increase of the prices. Here you have a chart as it went up at the end of 2010. So this was one aspect to try to save or to avoid rare earth magnets, so to have a look at other machine concepts. And another point at this time was you nearly always had 3 separate components in the drivetrain. You had the gearbox, you had the motor, and you had the power electronics. Motor and power electronics were 3-phase and they were separated. But this should be changed within the project with the focus on the motor development. There was, of course, this high system efficiency or for the whole system. Then developing now motors that are appropriate for an integration of the whole system and that are also appropriate for an automated production. Well, then, of course, rare earth magnets or expensive resources as rare earth magnets should be reduced or avoided in the project, and all steps during the development should address functional safety or intrinsic fail safety for the components. So how was this, or in which areas was this addressed? It's very fast. Okay, now. We had different layers or different working fields that have been considered, from the DC point and controller layer, software development following the ISO 26262, developments on the switching layer, that means driver developments, but also the power electronic devices themselves. And the actuator layer, they are having motors, of course, different kind of motors and different inverter topologies for several drivetrain concepts. But here I will focus on the areas of novel inverter topologies as well as the suitable motor topologies to this, and addressing or using innovative materials such as soft magnetic composites. So let's have a look at the different drivetrains or the different motor and inverter concepts that have been addressed. Well, there are 5 completely different machine concepts. Most concepts in this project come without rare earth magnets. They all have in common that they address intrinsic fail-safe machines, so that means a failure is dealt within the component, and they are all multi-phase. And for the inverters, it can be said all inverter topologies have been new or novel at this time. And in general, there are 2 small power units, so for distributed propulsion, and 3 developments for high power as a central drive for e-cars. One permanent magnet machine with ferrites. There I go into detail. Then an electrically variable transmission for a hybrid electrical car, and a synchronous reluctance machine from Spanish partners within the project. And they have in common that the concepts address the cost reduction. With the safety aspects, cost and convenience should be addressed, and the multi-phase is used as a basis for high integration, and with this weight, volume and cost are addressed. It's very difficult to use this pointer. Okay, now. So within the supply chain 2, where this demonstrator was built up, we addressed a pure electrical vehicle, class 1 to 1.2 tons, and we wanted to avoid permanent magnets completely, but staying with a permanent magnet synchronous machines, and therefore the potential of ferrite magnets was investigated. And additionally, this drivetrain should be completely integrated, but to this I'll come later on. So at first, integration in general, what do we understand there? Or within this project, we took a series housing with integrated gearbox, you see in the middle from one project partner, and in this housing with also integrated cooling, we integrated the electrical motor, all control elements coming from the project partners, the sensors, current position sensors, the switching elements, passive components as capacitors, and in parallel a power supply or DC battery supply was developed, and all these components were ready for car integration, but this is explicitly out of scope for this project, this integration. So with this, let's come to the so-called, or as we called it, key technology integrated multi-phase systems. Well, what does it mean? Everybody, if you knows probably the normal 3-phase systems as you have it for nearly all industrial applications. So then what is multi-phase about? Here in this context, if we talk about multi-phase, we mean more than 3 phases. And typical concepts are there 5-phase systems, 6, 7, 9-phase systems. They can be split. 5 and 7-phase are real, so-called real multi-phase systems, as 6 and 9 are only double or triple 3-phase systems. And for the project, it turned out that a 6-phase solution or 9-phase solution would be the best choice in terms of cost, power density, and also the efficiency of the whole system. And safety can here also understand as redundancy. If you have a triple 3-phase system, you have in a failure more remaining complete systems. So, but why is this multi-phase approach advantages for this application? Well, in general, for the EV applications, success factors are cost and compactness. Compactness can be power density, it can be weight, it can be volume, it depends on how you want to express it. If you then go over to a multi-phase system, so from 3 to 9 phases, you reduce the phase power and also the phase currents by the factor 3. That means you get much smaller power per phase. For the power electronics, that means you get much smaller power electronic devices for one phase. With these smaller devices, you have a much higher degree of freedom to distribute them in the space of the motor housing. So this means you can realize a very highly integrated system much more easily. By doing so, if you integrate the motor, the inverter into the motor, together with the gearing into one housing, you have only one common cooling system for all components. By this, you reduce the interfaces and also the parts you need very much, so you can save expensive, heavy, long cables, especially for the high current and high voltage connection you have typically between a three-phase inverter and a three-phase motor. They can be left out, and you don't need additional housing components for the inverter, as it is one part of the entire system cooling. Well, and by doing so, by reducing these components and these interfaces, you save a lot of volume and weight, and of course, as there are less parts, you also can save money or save costs. And so you come to innovative and competitive products for EV applications. So here an example how you can imagine this. Well, if you have a classic three-phase system with motor and a three-phase connection to the inverter, you can attach the inverter to the motor, but you don't save the cables, you don't save the interfaces. That means you don't have a real integration in this. But if you go over to this multi-phase concept, you have here your 9-phase inverter on a very flat shape, and you can integrate all this into the motor, and there you get a real system integration by doing so. So with this, I will come to the details how we did it in this project for supply chain 2. How did we realize the integration? Well, the demonstrator you will see at the back of this area here later on. From the right to the left, we start here with a gearbox that is integrated, or gearbox with differential, in a housing with integrated cooling. Into this housing, we designed an e-machine with a segmented tooth coil winding and with a ferrite rotor, so permanent magnet machine, but based on ferrite magnets. And for the integration, for building the cooling system for the inverter within the machine, we took the bearing plate of the motor and used it as well as the cooling base plate or the cooling system for the inverter. So the power modules or the power board is directly attached to this bearing cooling plate, and then you have the driver layer and you have the controller layer. And all this is integrated into one component. So, but coming more in detail to the motor, there are two different motor concepts. One concept was with a claw pole rotor, or claw pole motor with a claw pole rotor. There were built SMC claws, so with the soft magnetic composite. It's an isolated iron powder which can be pressed into nearly any shape. And their ferrite magnet slices or discs were used. The stator is a segmented tooth coil winding with 18 slots, 16 poles, and realized as a 9-phase winding, and also can be used as a 3-phase winding, but we did it as a 3x3-phase. But this concept only was used as a technology demonstrator for smaller power, so only more than 40 kilowatt in the constant power range. And then the other concept, where you can see also the rotor at the back of this area, we have buried ferrite magnet blocks that are within the rotor, the same 18-slot 16-pole winding. Here a flat wire winding is used. Michael Lambeck will introduce this later on more in detail, the winding design. This demonstrator, so with the same external dimensions, was used for much higher power, for a peak power of more than 55 kV, and this was realized to fulfill the specifications given from our OEM partner. So why this 3x3-phase winding? What is the use of this in terms of motor? So not only integration aspects, but also performance of the motor, of course, was addressed. So by doing so with this 18-slot 60-pole winding, you can increase the so-called winding factor from nearly 95% to more than 98%. That means you have an increase of roughly 5%. It means you get more torque with the same current if you drive the machine in a pure permanent magnet mode. And additionally, the torque ripple is reduced, which is in this winding configuration already low. You have here the blue line, and by shifting it to the 3x3-phase winding, the torque increases and the ripple decreases to below than 2%. and also losses as we address efficiency. Losses is a big topic for e-machines, especially for high speed. So therefore, with the shift, we addressed iron core losses. Normally this winding 18-slot 60-pole generates a lot of harmonics, especially subharmonics that produce a lot of losses in the rotor. And by coming to the shifted 9-phase winding, we can cancel these harmonics, especially the subharmonics, and that means we decrease especially the rotor losses significantly. So in the area of about 50%. If we look here exemplarily as a loss distribution in the rotor at the same working point, left is the 3-phase, right is the 9-phase configuration. You see there that the areas of high losses go down. It's only in a qualitative way here. Well, then let's come or have a look at the ferrites. As I said, we used ferrite magnets. Why did we do so? Well, there are two advantages and two very big disadvantages. The main advantage is, of course, this material is very cheap. The raw material for ferrites, and you can find it all over the world. So you have a long-term supply guaranteed and not only some single suppliers. But on the other hand side, with this material, you have a pretty poor energy density compared to rare earth magnets. It's only about 1/9 of the energy density. That means 1/3 of the remanence and one third of the coercitive field strength. And with this, you can very easily demagnetize the magnets, and that's what you have to avoid in a motor to run it. So therefore, special topologies of the rotor are needed to avoid the magnets from demagnetization and also to achieve a strong or a usable flux density in the air gap with these pretty weak magnets. So how was this done? So we built up or designed and built up a 60-pole PM rotor. And here it's a self-containing IPM rotor structure, so with no bandage. For speed, running speed with 11,500 RPM, that means a testing speed of more than 13,000 RPM. And the design was done in a way to integrate the maximum possible volume of ferrite magnets to get as much energy into this rotor as possible. And as ferrites have a lower density than rare earth magnets and also than iron, the rotor even didn't become that heavy, even having such many or such a high quantity of magnet volume inside. Well, the disk inverter I mentioned already. Here on the right side, you see the side of the inverter that's turned to the motor. Here you have 9 power modules, and directly on the other side of this power board, you have the 9 DC link capacitors. So a very short connection. It's space saving. This approach or this concept, and you get a very low inductance between power modules and DC link. So with this you can further reduce the DC link capacity that you need. And you can use standard modules, as now the power decreases very much per phase. So you have only 1/9 of 55 kilowatt to deliver. So with this we have the power board, then the inverter board, the driver board and the controller board. You can take it and very easily integrate it actually into the e-machine. So the outer diameter of the stator core and of the inverter could be chosen the same way or in the same size. So with this, what are the benefits now? Well, we can save with this 9-phase integrated approach, we can save the inverter housing completely, just make the motor housing a little bit longer. Then we can save this 3-phase high voltage, high current connections and the 6 plugs that we need for this completely. We have there only very small plug connectors that don't have to be isolated. Michael Lambeck will present you with the winding. Well, then the price uncertainties of neodymium iron boron can also be avoided or overcome by the low-cost ferrite magnets. Winding losses to limited voltage that you normally have and you need very high currents can be dealt in the way that you have every phase, now 9-phase, directly connected to the DC link, so more voltage per winding, and lower currents, lower wire diameters. All the winding factor can be increased, and the typical winding connections goes to a smart plug connection. So with this, I want to give you a short summary. Well, we had at first, the improvements in the electronics and power electronics that made it possible to address or to consider novel motor and also integration topologies. We needed enough calculating power to have this 9-phase control and also smart devices that could be integrated in this way. So therefore, we could do this transition from 3-phase to 9-phase, which favors then the system integration as it delivers more degrees of freedom for the design of the whole system. Well, with this, we addressed a strong reduction in weight, volume, and also in cost for the whole system. And of course, for such an integration and a holistic system approach is necessary. You can't any longer optimize only motor and inverter and put it then together. The whole system has to be optimized. So it can be said, on the first view, you have an increase in complexity or in the component complexity by now this 9-phase solution, but in the end, you get a much more simple system. As it is a completely sealed system, only DC connection to the outside, 1 water or 2 water connections, and a communication bus or communication connection. So with this, we could achieve improvements in efficiency, power density, cost, and also safety aspects as the component is completely sealed. Okay, with this, I come to the end. Thank you very much for the attention, and I hand over to Michael Lambeck.
Thank you very much, Yves. Thank you, ladies and gentlemen, for attending this session. I would like to go into a little more detail about the winding of the machine that was used in this demonstrator. But first of all, let me introduce EGSTON in a few short words. Okay. EGSTON is a family-owned business with headquarters in Austria and production in Czech Republic, China, and India. And we have 4 material groups that we produce: inductive and automotive components, mostly wound components, then cable systems and power supplies. If you would like more information, please visit our website. The address is given here. Now for the MotorBrain presentation, what were the challenges? Yves already pointed out quite a few challenges. One is high energy density with low losses, and in order to achieve that, we require a very high copper filling factor in the motor while keeping the thickness of the wire to the minimum to reduce losses. As Yves pointed out, the machine will be running at 11,500 RPM, so that is quite some speed. The second challenge was the integration, as Yves pointed out. So we want to have a very short connection from the motor winding to the inverter. And last not least, this high energy density requires some cooling. So we had to optimize the motor for the heat dissipation. Let's start with the first topic. I already pointed out copper filling. What does that mean? Oops. I see what you mean. A definition of the copper filling factor. The copper filling factor is the percentage of the total available winding space that is used by the copper wire. So as you can see here in this picture, the copper takes only part of the space. The rest is used by the outer insulation, typically the coil former, the air between the wires, and of course the wire insulation itself. If you do a normal thin wire winding, you typically get filling factors in the area of 40%. If you do a really good layer winding, like depicted here, you can go up to 70%, but we will see later that with our winding we could go even beyond that. What possibilities do we have for winding, and what are the advantages and disadvantages of each one? The easiest, of course, is to use just one thick copper wire and wind it like shown in a layer winding. Advantage, of course, if you have only one wire, the wire is cheap. As the diameter increases, the copper weight per kilogram decreases, so that's the cheapest wire available. And you get a relatively good filling factor. On the other hand, especially at those high speeds, you have high AC losses due to Skinner proximity effects. You can overcome that a bit by using a layer winding of multiple thinner wires. You see, it's still cheap because it's simple round wires, and the skin effect is reduced because of the thinner diameter of the single wires. But you need a special winding process to put each wire where you want it. Another possibility, if you're interested in the skin effect, is of course to use a Litz wire. But Litz wire is quite expensive compared to other types of wires, and you lose filling factor because each of the strands of the Litz wire has their own insulation, and you have a lot of air between the wires and possibly some silk or other insulation around the Litz wire, so filling factor is not optimal. Another possibility to get low AC losses is to use a foil winding. Unfortunately, there again you have a very bad filling factor because of the insulation material needed, and also the connection is a problem here because you have to solder or weld some connection to this foil to connect it then to your converter. And last not least, you can use a flat wire winding, especially if you do an edge winding. You have a very good filling factor combined with a good heat dissipation. I will get to that later. Of course, there's also disadvantage. The production cost to set up this kind of winding is higher than for a standard winding, and the flat wire itself is more expensive than a round wire, although not by so much. For the MotorBrain, we did two stators. I will explain later why there are these different stators. The first one is, as already mentioned, the flat wire winding, and the second one is a so-called two-wire winding. That means that, of course, they all look the same, but we have two wires wound in parallel, and by this we can get a very good filling factor of the available space and have a higher number of turns than for the flat wire. What are the advantages and disadvantages of each winding? Well, the flat wire has a big disadvantage, as already pointed out. The winding process is more difficult and so more expensive, especially the investment, the winding machine and the whole setup is more expensive than for a standard round winding. But it has a relatively low eddy current, so the AC losses are low if you do the edge winding, because you only have to consider the thickness of the wire and not the width. The filling factor for this project we could get above 75%, so a very good filling factor. We could get a lot of copper into our slots, and also the heat dissipation is very good. If you look at this picture, you see that every single wire touches the stator, and since the motor is cooled on the outside, the water cooling is outside, we can get the heat quite effectively out of the winding to the environment. Unfortunately, there are restraints. If the number of turns has a certain ratio to the width available for winding, then we can use a flat wire winding. Otherwise, we have to go to a different topology. And for the second demonstrator in the MotorBrain project, we use this two-wire winding. Here, it is very important that you position the wires where you want them to have, once again, the good filling factor that is required for the efficiency needed. But if you do that, then your filling factor is a lot better than for a single wire winding. How is that? If you look here, you see that there's a lot of air that you cannot use for a single wire winding, whereas if the wires get thinner, you have less air in the winding, so the filling factor is quite good. Also, the eddy currents are lower because your strand thickness is less than for a single wire winding. But again, you need a special winding system to get these wires in position as you want them. The second challenge, as mentioned, was the integration. So what did we do to make a good integration into the winding, into the whole motor, into the drive? What we did is that we used the ends of our flat wire winding and led them around the stator to the connections here. So we have no in-between connections of any kind. The winding wire itself, the flat wire, is directly led to the connection points, and then it connects to connectors here on the power board. This is the power board. You see the 9 power modules, and on these power boards we have connectors where the winding connection goes directly into the power board. So very short connection, very easy connection. It just plugs together. You can see it here. Those are the teeth, or the ends of the motor windings, and they'll go directly through the cooling into the power board. So the system integration is very good, and of course the less connections you have, the less winding length you have, the lower is your losses due to all these connections. Finally, we have the topic of cooling. As I said earlier, especially for the flat wire winding, each copper wire touches the stator, so we have a very good cooling. And by applying a special varnish, we could even improve the cooling, so we could get down to about 0.6 Kelvin per watt from the copper to the water cooling, to the housing of the motor. And for this type of motor, I think that's quite an impressive figure, because we could reach our goals, we could keep the temperatures over the whole operating range of the motor within the limits permitted by the winding. So, to sum up, we had those topics on our agenda. To increase the filling factor, yes, as we've seen, we could do that. To reduce the losses, we found out that the losses are quite favorable. Integration into the system, I've shown you this integration, so yes, we can say we achieved that. And cooling of the stator, so the goals have been achieved, and we think that this is a very good solution to further improve the efficiency of electrical vehicles.